How do we find out if this is a redox reaction? We find the oxidation states of every element and see if any of them changes. And if one changes, there's going to be another. You can't have just oxidation. You can't have just reduction. They have to go together. Because remember, it involves the transfer of electrons from one species to another. One gains, one loses. Okay, so here we go. I'll let you guys do this. Determine the take 32 seconds and find the oxidation state of every element in that reaction. Okay, we're done, right? Okay, over here. Well, I don't know. Where do you guys want to start? I know the easiest one up here is like this one, right? What is this? Excellent. Pick another one. Methane. What is the hydrogens? That means the carbon is. Okay. Over here. CO2. That means the carbon is. Ooh. And over here. -2 and +1 each. Is this a redox reaction? Did anything change oxidation state? So the carbons did what? Oxidized by losing or gaining? Lost by losing 8 electrons. What reduced? The oxygens reduced by gaining each gained 2. Would you agree with that? And so that's what we can use to help us balance the equation, because the electron transfer has to equalize. Here we have a species that lost 8 electrons. Those 8 electrons have to go somewhere. They have to go to something else. They have to go to the thing that's gaining the electrons. In this case, it's oxygen. So somehow or other, we got to account for more electrons. How can I do that? Okay. That accounts for 6. What's that? So it gives me 4 oxygens that have gained 2 electrons. There's my 8, right? Would you guys agree with that? Okay. And then to balance that out, I'll just look here. Does that make any sense? That was, first of all, you guys probably had that balance in your head before we ever started the whole process, because that was a very simple reaction. That's okay. But do you see how we can use the electron transfer to help us balance the equation? All we're trying to do is balance the electrons. That's all we're doing. Okay. That was our first little introduction to that. Let's try another one. Is this a redox reaction? First of all, a precipitate forms. What is that precipitate? Go ahead, Aaron. Say this again. Okay. What? Okay. How do you know that? Right. Okay. Is this a redox reaction? Paul, what did you conclude? It's not? Why not? Yeah. Oxidation states all stay the same. Over here, the magnesium's +2. This is -1 each. This is +1, +1, -2. You guys all felt comfortable with that? Over here, the magnesium's +2, +1, -2, +1, -1. So it's not a redox reaction. What is it, just for fun? You used to call it a double replacement, but now we also know that it can be called a precipitation reaction, right? Okay. So it's not that hard. You're looking for a change in oxidation state. All right. Well, I've kind of already introduced to you by that first reaction on how to use the oxidation states to balance equations. And it comes down to looking at how many electrons were transferred in both the oxidation and reduction and equalize that transfer. It's a really good starting point. Many times it finishes the reaction, the balancing, but and a lot of times, though, it's a good starting, because a lot of times, you guys may remember when you learned how to balance equations, you didn't even know where to start. You were bouncing around back and forth for like 5 minutes, okay? This will give you that good starting point, and they just make a couple little adjustments. So let's try one. It's relatively easy yet. We'll start off with a relatively easy one. Whoa, that's not right. Okay. So the first thing you should do is look at determine the oxidation state of each element. So how long for the boot, Megan? There are a lot of boots and crutches in this building right now. Ooh. So what are you in right now? Cross country, right? Or what are you out of right now? Be a better question. All right, what did you guys get for the manganese and the manganese dioxide? Aluminum is 0. The oxygens, -2 each. The aluminums and the manganese. Is that what you got, Dylan? Excellent. Okay, did anything oxidize? Is it a redox reaction? Yes, the manganese went from a 4 to a 0, and the aluminum went from a 0 to a 3. Okay, so we're going to use that. So the manganese, what did it do, actually? Reduced by 4 electrons. The aluminum oxidized by 3 electrons. Is the electron transfer equalized? It is not. So many times what we're going to do is find the lowest common multiple of those two, which is 12. So we want to get 12 electrons to be transferred. In order to do that, we're going to have this process happen how many times? 3. So we're going to multiply this by 3. And we're going to want this process to occur 4 times. But we have a little snag in there. We've already got 2 of them represented over here, right? So we're going to put a 2 here and a 4 here. Does that make any sense? So if you look at that, 4 aluminum atoms lose 12 electrons, and 3 manganese atoms gain 12 electrons. See where I'm going with that? The electron transfer is equal. Then you just go back and make sure everything else balances out. Okay? Well, we've got 6 oxygens here. We got 6 oxygens. Oh, we're done. So that's the whole point I was trying to make. Is a lot of times that's it. You're done. Okay? Now, could you have balanced that anyway without doing this process? Absolutely. But you're going to find out here in a really quick bit that may not be as obvious. So, all right. Any questions so far? Jacob, how's everything? How's Florida? It was good? Okay. Nice and warm? Were you on the beach? Gulf side or the ocean side? Okay. I like the Gulf side a little better, but, you know. All right, next. Okay, we're going to be throwing some wrenches into the thing now. Oh, yeah.
Ready for wrenches.
Yeah, ready for wrenches? You're not ready for wrenches yet? Look at your brain. Oh, look, her brain just exploded. I saw it happen. What? I was watching. I don't know if I have one. It's okay. It's okay. You'll be fine. I was watching the process happen, though. Yeah. Okay. I was keeping my eye on you. It was slowly building. It was directly related to the color of your face. No, I was watching the redness increase. It just did again, didn't it? Just playing, just playing. All right. So already, why is this one different than any we've looked at so far? How is it different? Okay. They're all ions. How would we classify the way this equation is written? Say this again. No. How would we classify the way this reaction is represented? Say this again. Net ionic. It's a net ionic equation. It's only showing the species that are involved in changing one way or the other. What's missing? Come on, come on. The spectator ions. What brought the manganese to the whole party? Who knows? It doesn't matter. Probably not oxygen. Probably not oxygen. But maybe a chloride ion, nitrate. It could have been manganese nitrate, manganese chloride, something along those lines. You guys see where I'm going with that? What brought the bismate ion to the party? What's that? Something. I'm asking specifically. Name an ion name a compound. Potassium bismate, sodium bismate, something along those lines, right? Because we know those will not participate in the reaction. And then, so now we got maybe some nitrate and some sodium ion in here, and they're just floating around. And so the nitrate, if we were going to like evaporate this stuff, would end up with the bismuth. The sodium would end up with that. You see where I'm going with that? I just didn't want you guys freaking out. Okay? Next, is this a redox reaction? Do the oxidation numbers change? Manganese starts off as +2, -2 each. The bismuth, therefore, is +5. Over here, the oxygens are -2 each. Therefore, the manganese is +7. And the bismuth over here is +3. Somebody hasn't asked yet. That usually draws, for the last 20 years, has drawn a question. Oh, no, that's not the question. Okay, usually at this point, students ask, Mr. Lehman, you wrote the charge as 3+, but the oxidation number was +3. That's the convention. Charges, you write the number first, then the sign. Where the oxidation states, you do it the reverse. Usually that's the question that happens. All right. Next, did the oxidation states change? Yeah, so what happened? The manganese oxidized by 5 electrons, whereas the bismuth reduced by 2 electrons. Would you guys concur? Okay. What's the lowest common multiple of 5 and 2? 10. So somehow or other, we have to squeeze a net transfer of 10 electrons. The bismuth, we're going to multiply by 5. The manganese species, we're going to multiply by 2. By doing that, not only have we balanced the manganese atoms and the bismuth atoms, we've also equalized the electron transfer. Would you guys agree with that? This process happened twice for a net of 10 electrons that were lost. This process happened 5 times for a net gain of 10 electrons. Hunky-dory? Awesome. But now we run into an issue that we haven't dealt with yet. Yeah, what's our problem? Oxygens are unbalanced by a lot. By a lot. Which means now we're going to start fiddling with everything else. But wait, maybe there's an easier solution. What if this were done in acidic solution? Just starting to... I don't want to. Okay, then balance it. Right. So anyway. Remember, you can't add anything to a reaction to get it to balance if it's not there. Many of you, well, some of you may have tried to do that whenever you were like freshmen learning how to balance equations. Oh, I'll just add more of this. Well, you can't do that. Okay? You can only include in the reaction what's present. Okay? Where is this reaction taking place? In what medium? It's an aqueous solution, meaning what's available? Water. What does water have in it that we could use right now? Oxygen. Okay? So over here, we have how many oxygens? 15. I thought I heard a 10. 15. How many oxygens over here? 8. We're missing 7 electrons on the right-hand side. So let's add 7 water molecules, because they're there. Okay? But now what's the issue? Now we have a bunch of hydrogen sitting around that we didn't have before. Oh, but wait. It's an acidic solution, meaning there's a bunch of extra. Remember, if we have a strong acid especially, we got a bunch of hydrogen ions floating around because it completely dissociates, right? Okay, so we can use that. And so where am I going to need that hydrogen? On the reactant side, how many? 14. There we go. Now, there is something that I forgot to do on the previous 2 reactions. No, I guess I didn't. I'll do it here. Okay, so here's the deal. When we're balancing redox reactions, not only do the atoms have to balance, clearly, the charge, the transfer of electrons has to balance, okay, and the net charge of the entire reaction also has to stay balanced. You can't have an increase or a decrease in charge. So that's kind of a nice little check to see if you did everything right. Well, we can clearly check the atoms because we've done that before. We actually made the atoms balance. You know what I'm saying? Now we just need to check the net charge on each side of the equation. So, looking at this side, what's the net charge over on the reactant side? Well, we have 14 positives plus 4 more, for a total of 18 positives, 5 negatives, for a net plus 13 on this side. Over here we have 15 positives and 2 negatives with no charge over here, so plus 13. That's nice, a nice little check to make sure that everything worked out okay. Where are the places you might screw up? Right here. You guys have a tendency, for some reason or other, not to write the charges with your ions. I've seen it before already, this year, okay? That's where you're going to screw up, okay, is forgetting to write your charges and then therefore not accounting for it. Valerie, how'd that go? Better than you thought it was going to. You need to come in. That'll happen. All right. Next, let me give you one to try on your own. Okay, here we go. I found one. No, that's not it. Nope. Go.
Okay, so when you added the charge from the right, like the total charge on the right,
Uh-huh.
add on the right side of the equation.
The 7 waters?
No, like you did the 15 plus, I got that from the business, and then
This?
but you did, yeah.
That's not, I don't care about that. The only thing that allowed me to do is find out whether it was a redox reaction or not, to help us figure this out.
Okay.
Because the manganese went from 2 to 7.
Okay.
5 electrons.
Alright.
Okay? All right. I'll find one for you somewhere. Give me a second. I'll find one. I could do that. No. Save that. No more there. All right, ready, set, go. Bless you. Ooh, my second favorite, thank you. There's not very many in there. Did you get it?
No.
Okay. I've never seen this reaction before in my life, so we'll do it together. Is it really? Okay. Let me see. 6, 2. Over here, it's 12, 10. Ooh, that's weird. Now what? I don't know either. I'll have to figure it out. Is it a half? It's not a half? What is it? No, I mean, is that what it is, though? Okay. 12, 10, 10 divided by 4. Is that what you came into? 10 divided by 4?
Yeah.
So isn't that a half? 2.5? I'm just asking, is that what it is?
Yeah.
Okay. So double it.
Double everything?
Sure. Isn't that what we used to do? That takes care of that, though, doesn't it? Howdy, howdy. Okay, so what'd you guys get? Sulfur you got +2 each. Is that what you got? Okay. Iodine you got -1 each, or -1. And over here we had -2 each. And then over here we had I know, but we'll get there. What do we initially get? Which is plus 2.5 each. Fractions. Anyway, is it a redox reaction? Yes. Not by much, but it's a redox reaction. Right? So what happened? Do the easy one. Right, iodine reduced by 1. Okay, that's why I said do the easy one first. And what happened to the sulfur? Oxidized by 0.5. What are we going to do? What are we going to do to get the equalize the electron transfer? One is the lowest common kind of thing, right? So we're going to have to multiply the sulfur by 2, which kind of makes sense, doesn't it? But wait, we might have to do some other things, because what's our other issue? The iodine's already at 2 here, so we're definitely going to have to do that, right? So that means there's 2 electrons transferred there. So the other ones have to go to, right, to get to 2. Would you agree? All right. But if I do this, will that be enough? I get it, but is the electron transfer balanced? Remember, that's the whole goal of what we're trying to do here. So we've got 4 atoms of sulfur. 4 atoms of sulfur. Each of them we're losing half of a charge 4 times. That's 2. The iodine transferred 2. By gain 2. Are we good? And that's why I actually I'm going to add this to the repertoire for the rest of the time, because that really, remember that point of emphasis I tried to make right there at the end of the last one, where I said the whole point of this is to balance the electron transfer? This is a great application of that. There really isn't kind of one here. So we actually had to deviate and think a little bit. Say this again. Okay, because we know we have 2 iodines. Okay, so we have to do that. Okay, well that puts us at 2 electrons being gained. Has to happen. Okay, so now we've got to lose the equivalent of 2 charges, 2 electrons. Okay, and because there's only a half involved, we have to have that process happen 4 times. It already does happen 4 times just by doing this. Remember the other idea I said it gives you a good starting point? It gave us a good starting point. Now, are we done? Well, do all of the atoms balance? Are the oxygens balanced? Right. What's the last thing we have to check? The charge. What's the net charge on the reactant side? -4. What is the net charge on the product side? -4. Boom. You're done. Valerie, better? Yeah. Megan, better? Or were you good to begin with?
This is the first time I'm actually grasping.
All year?
Yeah.
Okay. Nice. All right. Well, here's where we are. We got 3 minutes left, I think. Is that right? You guys tell me. Right. So the next piece is balancing in using the half reaction method. Okay. Let's reiterate what I was going to say. For the AP exam, this is the fastest way to get redox reactions balanced. You just look at the oxidation states, boom, 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 done. And it's going to show up every year in the multiple choice especially. They'll have at least 2 or 3 of these things where you just have to. Now, you could do it the half reaction method, which I'm going to show you next period, but that takes like 2 or 3 minutes to go through each one of them, or longer, okay? You can't screw it up, but it takes time. And remember, in the AP exam, you're kind of time limited there, okay? So I'd get really comfortable with this if I could, or if I were you guys. The half reaction method, though, you can balance anything. In fact, there's a little challenge problem I'm going to give you guys. What's today? Tuesday? Probably Thursday. We're talking coefficients in the double and triple digits. Okay, so, and like I said, the only way to do that is with the half reaction method, but we'll learn here in about 5 minutes. Anyway, I guess where I'm going with this is, if you want to take a little break now would be the time to do it, to get your brains a little recharged. And then we'll come back in like, what, 3 or 4 minutes? All right.